Hello children, today we are going to learn about applications of electromagnetic induction which we learned in the previous video lesson. We know that electromagnetic induction is nothing but whenever there is a change in magnetic flux linked with the coil, an EMF is induced in the coil that in turn produces current in the coil. Okay, that means to say here if you take a simple copper coil and connect it to a galvanometer, and if you change the magnetic flux which is present all around this coil continuously, then there will be a continuous flow of current in the circuit. So here either you can change to change this magnetic field, either you can move the coil towards the constant or stationary magnet or stationary magnetic field, or you can change you can move the magnet so that the magnetic flux linked with the coil can be changed. So either of these two we can produce the current in the coil. So that is called as electromagnetic induction. So we learned in the previous class like various ways of producing current we have seen, like either by moving the magnet or by moving the coil. So there must be a relative motion between the two objects here. One is a magnet or the coil here. So in any of these cases, the magnetic flux linked with the coil changes. As a result, the current will be induced in the coil. On the other hand, even we have seen the mutual induction. Mutual induction is nothing but here we are sending current through one coil and we are keeping another coil close to that the primary coil. So the second coil which we are keeping is called a secondary coil. So whenever we are changing the current which is passing through the primary coil, as a result the magnetic field which is developed around it also gets changed. As a result, this secondary coil is present in the changing magnetic field of the first coil. So the magnetic flux linked with the secondary coil is changing. As a result, the EMF is induced and in turn current is induced in the secondary coil. This is called as electromagnetic induction. So here we have seen in any ways we are able to produce the induced current. Current is generated in the coil with the help of magnetic field. So to understand in which direction this current is induced in the coil, we are using a rule called as Fleming's right hand rule. So take your right hand, Fleming's right hand rule. I am stating this rule. It's almost similar to the Fleming's left hand rule. So take right hand with these three fingers, thumb, forefinger and middle finger, in such a way that all the three are mutually perpendicular to each other. Okay, then the forefinger always points the direction of magnetic field and thumb indicates the direction of motion of the coil or the force on the coil. Then the middle finger indicates the direction of induced current in that coil. So we are going to use this Fleming's left hand rule to identify in which direction the current is induced in the coil. Okay, so I am going to write down the statement on the board. Please make a note of it. Fleming's right hand rule. It states that when the right hand, when the three fingers of the right hand, when the three fingers of the right hand, like forefinger, that is forefinger, middle finger and thumb finger, kept perpendicular to each other such that forefinger indicates the magnetic field Middle finger indicates, sorry, not middle finger, thumb. Thumb indicates motion of the conductor. Motion of the conductor. Then the middle finger indicates what it indicates? It indicates the direction of induced current in the coil. Induced current in the coil. So this is the statement of Fleming's right hand rule. So we are going to use this Fleming's right hand rule and also the electromagnetic induction in our day-to-day life. There are a lot of applications of this Fleming's right hand rule as well as the electromagnetic induction. So one of the such application is electric generator. We know that all these power stations always supply electricity to various houses or various cities or the factories, houses, everything. Okay, how are they able to supply this electricity? Are they having any big batteries with them? Definitely not. Yes, we know that we are generating electricity near the dams, windmills or thermal power stations. Yes, where we are using a turbine. That we learned in sources of energy lesson also. So we have a big fan like structure called as turbine. So whenever the turbine is rotated, that turbine is attached to a coil, and that coil will be rotated in the presence of magnetic field. Since the magnetic field is constant but the coil is rotating, as a result the flux linked with the coil changes and it induces current in the coil. So that's what we are able to store it in the power station. We are not storing it, actually we are transferring that to the various cities by overhead cables and all. Okay, so there are various ways of producing current, but in any of these cases we are using electric generator. So today we are going to learn about the functioning of this electric generator and what it consists of, what it is exactly, and what principle it works. Okay, electric generator is a device that converts mechanical energy into electrical energy. So we are doing a mechanical work there, and that mechanical work is converted into electrical energy. Mechanical work in the sense here, we simply just rotate the coil in the presence of magnetic field. That rotation is called as mechanical work. Okay, because of that rotation in the magnetic field, we can induce current in the coil. So how is this possible? So on what principle it works? It works on the principle of electromagnetic induction. Okay, remember this. And to identify the direction of induced current here, we are using this Fleming's right hand rule. Okay, so the structure, what it consists of inside, it is almost similar to the electric motor, where you have seen the electric motor is a device which converts electrical energy into mechanical work, but electric generator is quite opposite. We are using the mechanical work to generate electricity. Okay, so quite opposite, but the structure is almost similar to the electric motor. So when we are generating electricity, we have two types of electricity, like alternating current, and also we have direct current. So today we are going to learn about alternating current, how we can generate the alternating current, because most of the house appliances, all these house appliances or the factories use alternating current because it has got lot of applications in our day-to-day life, lot of advantages than DC. Okay, that we will learn afterwards, but as of now, how to generate this alternating current, that we are going to learn, and that is like a AC generator. So AC generator is the device which converts mechanical energy into AC, like alternating current. Fine. So it has this kind of structure. We have a strong magnetic field, a radial magnetic field, like we have a magnets like this with its north and south poles. Okay, and we are putting like this because it will produce the field radially in all directions. Okay, so we have a radial magnetic field like this, in which we are keeping ABCD, like you can see a wire, okay, copper wire, which is called as armature coil. Okay, so this is ABCD is the armature coil, which is kept perpendicular to that. Like field is like this, but the coil is placed perpendicular to that. Okay, and the ends of the coil are connected to two slip rings. S1 and S2 are the slip rings, not split, it is slip. Okay, slip rings. Why they are called slip rings, I will tell you a bit later. Okay, so here we have two slip rings where one end of the coil is connected to the one slip ring S1 here, and another end of the coil is connected through this to the another slip ring S2. And these two are attached to, these two are in contact with the carbon brushes B1 and B2. They are just in contact. B1 and B2 are not attached to it, but they are just in contact with these slip rings. So through this B1 and B2, we are connecting galvanometer to check whether the current is induced or not. Okay, so the deflection in the galvanometer tells us how much current is induced, in which direction current is induced. All these things we will come to know with the help of this galvanometer. So this is about the structure. Now coming to the working of this electric generator, how it works. Okay, now we have to we have to give the mechanical work. Okay, like mechanical energy is converted into electrical energy here. So we have to do a work, a mechanical work here. Mechanical work in the sense, this coil is attached to the turbine. We know that big fan like structure, that is called as turbine. Okay, that turbine can be rotated by various ways. I told you, either by passing high velocity steam on that in the thermal power stations, or flowing water, falling water on that, so that the kinetic energy of the water can be converted into kinetic energy of this turbine. So that turbine is connected to this armature coil. So whenever the turbine is rotated in one particular direction in the magnetic field, what will happen? Let us see this. Let us imagine this coil is rotated clockwise direction. Okay, like the arm AB of the armature coil is coming up and CD is going down. Remember, whenever the coil is coming up, it will induce the current in one particular direction. Whenever the arms are going down, it will induce the current in the opposite direction. So we are going to see this, how, in which direction the current is induced in this. For that purpose, what we have to use? We have to use the Fleming's right hand rule. So stretch these three fingers like this and apply the same thing here. And we know that the direction of magnetic field here is like this, from north to south pole. So I am putting this forefinger in the direction of magnetic field, and you can see the thumb is coming out because it is moving upwards for the clockwise direction. So I am putting my finger like this. Then what the middle finger shows, whatever direction the middle finger shows, that is the direction of induced current in the coil. So now see this. I am putting like this, in which direction the middle finger is showing? From A to B. That means to say, in the arm AB, current is induced from A to B. Okay, coming to the other side of the arm, that is CD coil. So CD. In the CD, now again same, the magnetic field direction is same. So put like this only. But the CD is going down. Am I right? So that the thumb should be in the downward direction. So I am keeping like this. So when I am keeping like this, in which direction the middle finger is showing? Downwards. That means to say the current will be induced from C to D like this. That means to say, whenever the coil is rotated in the clockwise direction, arm AB comes up. As a result, current is passing from A to B. And arm CD goes down. As a result, current passes from C to D. So A to B, B to C, C to D, and then it is coming to S2. From S2 to B2, B2 to galvanometer. So galvanometer will be deflected that side, and it is coming to B1 again. B1 to slip ring S1, S1 to again the coil. Okay, this is the direction of current. Now let us suppose it has moved to the half rotation. Okay, half rotation, 90 degrees. When it is coming to this position, after that what is happening? Further rotation when it takes, then AB is going to this side, CD is coming to this side. So when AB comes this side, what happens? AB goes down, CD comes up. I told you, whenever the arms are coming up, current will be from down to up. Whenever arms are going down, current will be like this. So when AB comes this side and CD comes this side, what happens? Opposite takes place. Okay, so when the coil is rotating, along with the coil, even the slip rings rotate. So this slip ring S1 comes this side and S2 comes this side. Am I right? It will move like this. When it is moving, what will happen? Now because S1 is this side, the current is passing from B to A through S1 to the B1 to galvanometer, again galvanometer to B2 to S2 to CD. So reversal is taking place. So the direction of current will be now like this. Whenever it is going down and opposite direction it is taking place. That means to say alternately current is changing its direction. So we call this as AC current. So in this way we are able to generate alternating current with the help of electromagnetic induction and with the help of this simple circuit. Is this clear, children? And if it is not clear to you, I will show the animated videos in the live classes, and there you can understand more clearly and you can ask me doubts if you have any. Thank you, children, for listening.